Okay, hello everybody. So thanks for coming to this lecture. So I'm going to talk about human action recognition. So I'm from INRAE lab in Paris. So INRAE, if you don't know, is a big organization in France. It's a computer science research institute in France. We are hiring as well, so if you are interested. Okay, so this lecture is about human action recognition. So I'm going to talk about several topics. More in the so I will finish with the more recent methods and actually the practical, which will end the session will be on implementing the one baseline on action recognition. So you get your hands on very recent methods, which achieve maybe not the most state-of-the-art performance, but close to it. Okay, and I'll start with more maybe earlier methods and even quite earlier methods. So where maybe first evidences where the history of human motion and human appearance analysis. So and it will progress with the time. So if you look back, so this is probably not the first evidence, of course, but this is one which is documented well by Leonardo da Vinci. So he was interested in human appearance analysis and motion analysis for the goal of teaching the students how to draw the people correctly. So, for example, he was saying that if you should draw the figures realistically, so the students should know about the bones, the structure of muscles, and the stresses, and so how a person moves in order to depict this realistically. So that was very important at that time, so a bit more recently. So there was a work by Giovanni Alfonso. In 1600, and so he was more practical. So he was studying the also human motion, but from the perspective of answering question how much people can work. So he was explaining what physical force, what physical work people do with the muscles, how muscle move, and so on. So basically, he was calculating how much people have to eat and so on. Now more closer to our times, so once photography was invented, so people started, of course, interested also in moving pictures. So these are the few first experiments done by Etienne Jules Marais and Edward Muybridge. So here are the one of the first sequences of motion which people have taken, and this is a particular experiment done by Edward Muybridge. So the experiment was supposed to answer the question. So when a horse is galloping, is there a point in time when all the legs of the horse are on top of the ground or not? So people didn't know before this and after this experiment. So it turned out that, I think, if I'm correct, so that there is no such time point. Okay, and of course the moving pictures. So if capturing sequences of pictures and showing them in a row, so we can observe the motion. So all this came up in the very early 20th century. So now even closer to our time. So this is already when computers have been invented. So Gunnar Jonsson, so he was studying the human perception of motion. So this is a quite interesting study for psychologists, but also which has motivated lots of computer vision research and motion understanding. So if you haven't seen this type of images, so maybe you can guess what these points represent. So how many of you can guess what this is? So maybe all of you know, or maybe all of you don't know. Okay, so basically, if you haven't seen these pictures before, so it's very hard to understand. So, but once these points start moving, so it becomes very apparent, and that was very interesting experiment. So actually, I have a video which was, so here is really a very old video from '71. It's original from people. I think there was from Cornell, and also so collaborated with Gunnar Jonsson in Sweden. So they so it shows the setup. So that's how they worked at the time, and so they were studying the motion of like simple dots and how people perceive these like very simple. So if there is one dot, so it makes an elliptic surface, and then if it's several dots, then they are grouped together. But then, more interestingly, so if putting the dots on the person, so the perception of human action becomes very apparent. So. Right. So what is interesting, actually, has motivated lots of research at that time in computer vision is that from very few measurements, so if you are able to capture these points on the body, from very few measurements, and at that time computers were slow, so people liked it. From very few measurements, this is evidence, you can recognize lots of high-level stuff going on. Fine. So here is a very short retrospective, and so now moving more to our time. So here is so looking at applications, what currently we are doing with computer vision and motion analysis and action analysis. So here's a movie everybody knows. So here, what's interesting is that they've been, okay, so this is an animated movie, but to make this movie look good, so they had to capture the motion of real people, and they had to do some very fine. So as you see here, so there are some vision system. This is a camera which captures the very fine motion on the human face, so that the movie looks realistic. Now, if we compare these Leonardo da Vinci and the new Avatar movie, so we see the interesting parallel that maybe the methods are very different, but the tasks, the applications which we are trying to solve are quite similar. So one of the major applications is in graphics currently. So we are trying to represent the world realistically, and Leonardo da Vinci was teaching students, and we are trying to program computers how to do this better. Well, of course, graphics is one nice application. So here is another example from a quite recent, 8 years ago, paper where we see video completion. So, for example, so maybe you've seen some methods on image completion. So this is an analogy that if you want to remove a person, so we can do it. And actually here the method is very simple. So it doesn't know anything about high-level person actions and so on. So so here is another example from Berkeley from PhD work of Alois Schäfers, and this is Greg Morey, at the time also a PhD student in Berkeley. So so Greg was very interested in football, and here is a final of Germany-US at some year, I don't remember when. So what happens here is that here we see the football field, and there is a Greg putting him on the real movie of the final of the football game. Okay, so basically, here is the video which has been taken in the lab or in the settings, and from this motion of the person, so it was transferred to this movie. Okay, so this is another just fun application, but it shows kind of what things are possible. So this, of course, done automatically. Now, so even more broadly, so if you want, so graphics is obviously a very interesting applications. So another application is recognition. So action recognition is interesting for many different setups. For example, for professionals or even amateurs who are trying to make maybe summaries or programs. So here is a type of human interactions. For example, this is a topic of this workshop. Summer school. So if you want to search for content-based video retrieval, this is obviously a big topic. There is a track video evaluation on this topic and many different things. So home entertainment. So this is with Kinect. So obviously this is, they're using depth sensors, but this is also an example of a vision application where we capture the human motion for interaction between the people and computers. So we came across, and we are trying to work on these topics, work in sociology. So they are interested, for example, in counting. So we've seen papers where people have, sociologists have hired PhD students to count, to watch through like thousands of hours of movies and to count how many times people smoked, the main actors smoked in these movies. And in order to infer how does it influence the adolescent smoking in society and so on. So obviously, if you could automate this task, this would save lots of PhD days and years. And surveillance, so obviously surveillance, we all know it. So people have good and bad opinions. So here is an example, which also you may have seen on YouTube. So here is a well, it's a real surveillance camera, but it was in UK private surveillance camera. So people were missing a cat, and they somehow they looked at this video for some reason, and they've seen this. And if this is your cat, so even if you don't like surveillance videos, so you definitely want to see this. And well, this is of course, surveillance video is boring and it's interesting in 0.001% of the time, but when it's interesting, it's interesting. So you want to find. And currently, basically, there are no methods which we can talk. We will talk later about this, but currently, there are basically no methods which could address this problem, and this is one of the big challenges. Okay, so another motivation why we want to look at human motion. So there is a very simple evidence. We can just try to count the pixels. So when you watch movie or when you watch TV, so you can imagine counting pixels. How many person pixels do you see? So it's like, so it says, so these are just random frames from movie, TV, and YouTube. So can you guess how many person pixels in this type of media do you see? In average, of course, if you average over the frames, in percentage. So is it 5%, 50%, 70%? How much? 70. Wow. Other guesses? So I thought it would be around 10, maybe 5. But it turns out that it's quite large. So it is around 35, 40%. And so this is on video, and so this is done maybe like taking random frames from 100 movies and calculating. So and on Flickr on static images, so it's the number is about 25. So what this says, this motivates our research where we look at people, because if you want to analyze all this data, so that we have another argument is that we have lots of data currently, so it comes from professional archives. So this is BBC, this is INA, this is the French equivalent of BBC. They record TV programs since, I don't know, from 60s, so they have lots of material. But YouTube obviously is even bigger, and surveillance, if one just accumulate all surveillance data, this is huge amounts which nobody can watch. So if you want to interpret this data, we obviously want to understand what the person pixels are doing. But another evidence, what I think is funny, is that we are very selfish, so we are very focused. The only thing we are interested in are people, actually. Okay, so this is good on the motivation. So I'm going to talk now about some methods, and I will start about poses, because poses is one very natural way to address analysis of humans. So like Leonardo da Vinci, so he was arguing about poses and how muscles and so on. So let's see what current research is doing in pose estimation and action recognition. So here are some examples from recent work. So these are real results, what current computer vision algorithm can achieve in these settings. So this looks quite impressive. However, I'll show, of course, the errors, more errors towards in the next slides. So why pose is interesting for activity? What is the link between activities and pose? So we can arguably say that pose and activities are very related, not always, but in some cases, so we can say that this person is thinking, this is some gymnastic exercise, so he is fighting and so on. So here's another example of very high correlation between activity and poses. Also in like now in photographs which we take from Flickr, for example, and here are examples from now Pascal challenge. So if you're familiar with Pascal challenges, they have this is the biggest object recognition challenge at the moment. So they also have a task on action recognition in still images, not in video, just in still images, where given the bounding box, for example, like this, so you are asked to write a program which will say that this person is phoning, and yeah, so all these people are phoning, for example, other people are cycling and so on. So, okay, this is a very hard task, but here we see that if we can capture the human pose, this would be quite helpful to recognize that this is what action the person is doing. Okay, so what are the challenges? So obviously we have lots of variation in poses, and as all computer vision scenarios, we have a problem of perceiving just the 2D image while the data is in 3D, so there are lots of information got lost on the way. Okay, for example here, so this is a very hard to interpret image. Actually, the person is with the leg towards us. Okay, I'm sorry. So maybe you should. Can you switch off at least the frontal light, if possible? Well, actually, this slide is supposed to show you the challenge. So one of the challenges is lighting. Okay, so so basically, if you have a dark image, this is hard, and right. So, but there are other things. So like all the typical things like in vision which we have. So the scale, the occlusion, the clutter, the clothing, the occlusion. So all this is very, very typical, very hard problems. Another problem with pose estimation is, of course, is degree of freedom, because if we are going to, so I'm showing in a minute how we can try to achieve, to address this task. If you parameterize the body, so body has lots of degrees of freedom. If you try to recover it, this is a very high dimensional problem. And noisy data. Okay, so one of the, well, probably almost the mainstream approach how to deal with human poses is to consider some kind of graph structure where you connect, when you present the body as limbs, and then you connect the limbs by some connections, and this defines the graph structure of your problem. So here is a very, very famous image from this paper. So it applies to pose estimation, but also for many methods doing object recognition. So the representation is the following, so that we have the parts, for example, eyes, nose, and so on. And also we have the springs. So eyes and nose, they could be associated with some particular representation, so how the nose and eyes look like. And the springs, they are here to constrain the relative position of parts. So this is a very natural representation. So basically, we want to put constraint both on the appearance of individual parts and on their spatial relations, so where they are with respect to each other in the image. Okay. So so I'll show in the next slide so how we can mathematically describe this model. So this model has been around for quite a while. So in '99, so they've been, and so on. There've been quite some attempts to recover the human pose. So in a sense that putting the rectangles for each limb on the image. And as you see, so it was, of course, these are successful examples, but usually the conditions were very simple. So they were static background. Usually was the method needed to have background subtraction. So it didn't work very well, but nevertheless, in some cases, it worked pretty good. So, okay, so how can we solve this problem? So, as I said, so one solution is to represent the poses as graphs. So we can assign the nodes of the graph to the limbs, and then to have a springs between the nodes. Okay, so nodes or vertices, they are defined at A, and the edges are the springs between the nodes is E. And so we can define the state space, so we can allow the position of parts to change, for example, anywhere in the image, and constrain the edges. So the solution space is really very large, because we have a exponential number of possibilities in terms of the number of limbs. Okay, because if they're independent, then it's exponential. So and this is a problem. So how we can put constraints, and how can we do the fast inference? So the constraints, as I said before, these are provided by the springs. So here is a so-called energy function, which is defined on the graph. And the energy function, it evaluates how the current state of the model, how does it match to the image. Okay, so if you have instantiation of body parts, so the position of body parts, so you can evaluate so-called unary potential. You can evaluate how good the appearance of each part corresponds to the image, and also you can evaluate how the relative position of parts corresponds to the model which is described by the springs. Okay, so here is a unary term and binary term. So maybe you are familiar with this type of function. So it appears in many different setups. So not only for pose estimation, but also for image segmentation, other tasks. So how many of you have seen this type of unary binary cost function? Okay, so this is a yes, very common way of addressing the problems, for stereo estimation or for image segmentation. So these nodes would be not the limbs, but these would be individual pixels. And the labels of the nodes would be, for example, the disparity value, or the label of, so is it like for this scene would be a house, a tree, and so on. Anyway, so so this is a graph formulation. Now, as said before, so if we are trying to brute force this problem, so okay, so here are some numbers. So if we discretize this state space, and so assign each limb to some positions and say 36 scales, so the solution space is huge, so we cannot possibly search through it. So the trick here, so why obviously people use it, so there must be a trick. So what's the trick? The trick is that if we consider the full graph, then the inference is very hard. But if we avoid the cycles, so if our graph is a tree or a dog, then actually the solution could be found very efficiently by dynamic programming. Okay, so these are very well-known facts. So I'm not going through them, but so if there is a tree, then you can just run dynamic programming on it, and this will find your solution in polynomial time. So this is very good. However, so this is not always good. So because if we are avoiding the cycles, it means that we are breaking some. So if we can, so here is the okay. Back to this model. So if to reduce the full graph to a tree, so obviously we have to break some links. Okay, and by breaking some links, we are removing some dependencies which might be important. And one important example of one such important dependency is, for example, modeling the dependence between the left arm and right hand and left hand. So here, so for example, in this method, the hands were modeled with a skin color. So if we don't model dependencies, it's frequently occurs that the two hands are merged into one, and so on. So well, I'm just saying that the tree has huge advantages for the speed, but it has some disadvantages for the performance. And There are also ways to run the inference on the cycled graphs. This is slower and also not exact. So here you get exact solution, here you don't, but you can do it as well. Right, so, and there've been quite some work on pose estimation. So I'm mentioning here a few papers. So from 2007, 8, 9, I'm going to talk a bit more about this work. And just last CVPR, last summer, so we had, I think it was at least 5 great papers on pose estimation by Yang and Ramanan and other authors. So this one is particular. So we've tried this. We are using this in our work, and so they have code online. So if you're interested in pose estimation, you can go to this page and get their code. So it works pretty good. So you can also retrain it on your images. Okay, so what differences between these? So all these 3 are in static images. So this tries to do pose estimation over time and get some temporal constraints helping the pose estimation. So there are some issues how to train the model. For example, where you get the training data, obviously you need. So I've talked about the inference, but actually there is another problem of how do you get this unary and binary potential. So usually you should, well, you can just set it by hand, and usually it works worse than if you train them. So, and to train them, you need lots of training data, means you need lots of images with manual annotated poses. And so manual annotation is possible but costly, and in large amounts, so it can be done in Mechanical Turk, for example. So people are doing this. Do you know Mechanical Turk service? Somebody knows? So okay, so this is Amazon provides computing power, but it also provides links the people with other people who do some work for you for small money. So, but the problem is that this annotation is usually quite noisy. So to reduce the noise, you need some additional methods. To and this paper, for example, does it. Okay, and this is a Kinect. Well, one part of the Kinect, which was also introduced last year at CVPR. So Kinect has the device is, as you know, probably it's 3D. It's a depth sensor, active depth sensor, and with this, so it's possible to now do very good pose estimation, pose tracking, which people now use for computer games, but also for lots of other applications. And the way how it was done, so it's described in this paper. So it was done also. So learning is a very important aspect here. So it was learned on lots of computer graphics generated 3D depth images. So there are curves in the paper which shows that the more training you give, as usual, so the more benefits you get. So it's important to have lots of training data. So here are some examples from paper 2009. So where, again, so this is a maybe more fun application, but it shows what is currently possible. So if you are defining a query, so if you run a pose detector over the whole movie and you define a query just by one image, so you do pose estimation on this one and assume you have run the pose estimator over all the frames, then you can immediately retrieve the poses like this, so which are similar to this pose. So here's another example of standing person. Right. Okay, and so I'm going to show another fun application, what you can do with pose estimation today. So again, pose estimation is still a very hard problem. So in the Kinect, so it works very good if you have a 3D data, but in RGB data, this is still a very hard problem. However, so if you in some setups, it works very good and you can actually use it. So here's an example from this CVPR 9 paper. What the goal is to, given the video with a sign language, so here's I guess a BBC TV News program with a person who is signing. Okay. So what are the input? This is the video, and also there are subtitles. So basically there is a annotation provided. Okay. So for each sign here, there is words. Okay. So the goal, what is the goal? The goal is to automatically train this, learn the sign language given this video and the subtitles. And this is the output of the system. So, for example, so it has learned that this is an office sign, this is a government sign. Okay, so how this was done? So, so it's interesting because there is really no manual input here apart from just providing the videos and subtitles. So everything was done automatically using the pose estimator. So that's why I'm talking about this here. So here is the example why it's possible. So so here is one sequence and of person signing and the pose estimated here. Okay, and sentence saying a tree. So maybe if you are given just this signal, so you don't know some language, so this will be very hard. Well, it won't be basically impossible to figure out where is the tree sign in this. I couldn't say it, at least. So, but the trick is that now if you don't have just one video, if you have many of them, then you can exploit the redundancy and try to, so because you know that all these videos, they should have the tree sign at least once in them. So you can try to search for a tree sign, search for a sign which is common between all of them, okay? So this is one idea. Another idea is so this would be a generative approach where you just try to search for a common thing. So now in vision, we have lots of evidence that just generative methods don't work very well. So we can also go for discriminative method. We can also use lots of negative data and showing the algorithm that, look, here there is no tree. Okay, and we can have lots and lots of these videos. And again, one of the key aspects is that maybe from 3 examples you would not be able to learn it, but because the data is very large, so if you, well, it's there, so we can use it. So it does work actually. Okay, I'm going to skip the details, but the main thing is about redundancy. Like if the method tries to find something which is common between these frames and never appears here. Okay, and eventually, so it converges to the correct tree sign, which is this. Okay. Okay, I'm going to skip this. And okay, so here is the. Now imagine you are a computer which is trying to learn the task of learning the golf sign. So if you can watch this movie and try to figure out what is the golf sign. So here are subtitles, here is the person signing. So did you get it? Okay. And in this way, so it is possible to learn lots of different signs, so completely automatically, as I said. So like signs with which are discriminated by hand shape, and so signs which is described by 2 hands and so on. Okay, so this is example where also I said, so the pose estimation in general is still a very challenging problem in images and video, but this is example where it actually works and can be useful. Okay, so where are the current failures? So the truncations is very hard. So here maybe it could be a model because we know this is an image boundary, so we could maybe extend the model just to it would be a bit more clever. But here actually, so if you would like to reason about occlusions in this image, so just looking at the people, which current methods are doing, would not be enough. We really need to know something about the rest of the scene. Like what is the occluding? Is this an occluder, or is it an error of my pose estimation? So people are currently actually looking at multiple people. So if we have a group of people and people are occluding each other, so the pose estimation is addressed in this setting. But in general setting of a scene where occlusions can happen anywhere, so this is still future. So, well, this is future, however, so there are some attempts to address people in objects. So, for example, here in this paper, CVPR 10 paper, so they try to model both the pose of person and the detection of objects. What they show that if they do two things simultaneously, the detection of this racket. So if they do it independently, I don't know if you can see on the bottom. So if they do it independently, the results are very bad. But they claim that if they do it jointly, pose estimation and object detection, of course, objects which are manipulated by people, like a racket, for example. So these two tasks are solved jointly, improve both object detection and pose estimation. So in other very recent work from last CVPR last year as well, so there is the attempt to try to model the scene and the people, or objects and the people. So here is a scene, and there is some geometric interpretation of the scene. So what the method is trying to do, they try to predict how people will behave in the scene, or more statically putting the poses into the environment and saying that these areas people can reach, for example, these areas people can lay, and so on. So there is not much semantics in this work, so this is a pure geometric reasoning, but this is an interesting future direction of interaction between the whole scene and the people, interpreting the whole scene now currently, but eventually dynamics in together jointly. Okay, so this is a part on human poses. So there is lots of, it's a very dynamic area, so lots of people are working on this. Still, it's quite difficult to do. And yet, so even if poses are expected to be important for human actions, so they are not human actions. So there is lots of other cues which we can explore to recognize actions, and also poses. So there is no one-to-one correspondence between actions and poses. So okay, maybe somebody takes over. Fine. So I've talked about human poses, so now I'm going to talk more about recognition in video. So that was, so far it was in still images, so I'm going to talk now about videos and appearance, and then motion-based methods. And so this will be the topic of after the break, the space-time methods. So what is maybe the most simple appearance method which you can imagine to analyze humans in video? So this is maybe one. Maybe there are simpler, but I think this is quite basic. So you can do background subtraction. So this is what people did from the beginning. And it works very fast. It's great, and it's in some cases it also works very good, but not always. Okay, so here is an example from late 90s of a method which does just this. So it does background subtraction every frame, and then also tries to reason about the temporal evolution of these shapes. So one way to summarize everything from multiple silhouettes into one picture. So they combine so-called motion history image, where each pixel of this image corresponds to one of the shapes here, and the color is the time. So how long ago did I see this pixel appearing in the foreground? So that's basically this image. And then, okay, there are some simple descriptors defined on this, like some moment, and there is a nearest neighbor classification on such data set of aerobics, which gives 66%. Okay, so this is something quite simple, very easy to do. So you can program it in half a day, and actually it has been used. So well, they've shown some applications for human-computer interactions. So where does it fail? So we can imagine, okay, so the good things about this is it's simple and fast and works in control settings. But so it can be very easily corrupted, and one potential problem is, so for example, the lighting, obviously. So if you have shadows, this corrupts the silhouettes. Also, background subtraction just sometimes doesn't work. So if you have the dynamic scene with lots of people, so there is no background subtraction. But even if background subtraction would work, I'm sorry again, so this is a image on the bottom here. So the silhouette of a person for these two actions, for example, if a person is drinking and it's a frontal view, so the silhouette basically doesn't tell you much. So you need some other cues. Okay, so silhouettes is not perfect. However, okay, so if we are still useful sometimes, so if people have tried to improve this type of methods, and one quite straightforward improvement on top of this is to say that not all shapes are plausible. So if you are looking at people, so we are interested just in human shapes. So we want to put constraints on how people actually look like and use these constraints for the interpretation. So, so this is active shape appearance models from Kutz. So it's now quite well-known methods. So how many of you are familiar with PCA? Good. Okay, so this is an application of PCA basically to shape analysis. Have you seen this method before? Okay, good. Good. So just briefly describing, so what you can do, you can parameterize your shape. So say you put manually you put some dots, say on the mouth here. So this is a simple experiment. You can do it yourself. And then your data vector is basically the coordinates, x and y coordinates of these points in the image. Okay, so you collect many of them, and so you can divide the mean shape and also the covariance of the shapes. And then you can say this is a 2D example. So you have a covariance matrix. So you try to find the main eigenvectors of it. Okay, and as usual, so the few major eigenvectors, they stand for most of the variation in the data. So you can describe the deformation of the shape with a very few components. So that's the main idea. And also, not just that your description is reduced, but also you can correct some errors. You can use it as a regularizer. So your shape space would say that this shape is unplausible. So if you project it, if these are your measurements, so you project them into your space which you have learned, so you can correct for errors. Fine, and also you can not just model the silhouettes, of course you can model anything inside the silhouettes like eyes and nose and so on. Okay, so that was quite useful. So one can also now not just model the shapes just in one frame, but also look at the evolution of shapes over time. So here is one simple model how the shape can evolve. So B's are now the parameters of the shape in the reduced basis coordinate frames, and so W is a noise, so one can govern the evolution of shape just by noise and apply some standard tracking, Kalman tracker or particle filter tracker. And here are some examples of this shape tracking. So now if you imagine just doing the background subtraction, this would be hard in this scene because there are some light variation and the variation of people in clothing and so on. However, so it's here it works pretty good. So here it was quite simple motion model. One can now do a bit better job. So if we know, okay, so what we've done here, so we've constrained the shape space. Now what we can also constrain the motion. So motion, for example, if you know the person is walking or running, so the motion is not random. So we can actually, instead of putting the just Gaussian noise for the evolution of the model, we can put some more sophisticated motion model and predict how given the current shape, predict how the shape will look like in the next frame. So this can be learned from the data. So if we have some good shape estimation over the frames, we can learn, in this case, a linear model. The model can be, of course, more complicated. In this case, it's a linear autoregressive model, so where you take your x, so x is a shape, and you project it to some matrix A to get the shape in the next frame. Okay, So it's a linear transformation, and the parameters of this linear transformation can be learned. Okay, so I'm not going into details, just to say, so here is an example of illustrating, in a 2D example of illustrating the idea. It's not people, so here are the axes. These are not the shapes, but just the points in the image. So here is somebody has drawn the word Andrew in the image space, and this is what the model, so learned the model from this data, and this is the model driven by noise, so it tries to have the same statistical motion as here, right? But so the model is not sophisticated enough to reproduce the word Andrew, but actually it does write something which resembles this evolution, temporal evolution. Okay. So one can do the same for, obviously, for example, gestures, like or motions, like here is the walking. Okay, so we can, given the one frame, we can predict how the silhouette will look like in the future. Also, so the we can combine. So if we learn different, we can walk, we can run, we can do different things. So now we can learn different models for each of these actions, and then combine them during the test. We can try to do the inference of both the position and the shape of the hand, for example, but also the model, so what kind of motion is going on. So here is a demonstration where the motion has been learned for 3 types of actions, so line drawing, scribbling, and idle. And we can see, so the color is changing, so we see that the system is recognizing, well, it is correctly tracking, but it also recognizes the correct type of motion. So we can also, for example, recognize signs, again, by learning different motion models, so we can do some interfaces, for example, and so on. So, okay, so I've talked about silhouette-based method, and also constraints which we can put on the shape and also on the motion. Okay, so these are interesting directions. So the advantage is that we can do more accurate tracking and with specific motion models, and we can do also simultaneous tracking and also model estimation or action recognition. So these are the good things. So the bad things are still that, so if, as in all tracking methods, so tracking methods are prone to local minima. So if the tracker gets lost, so it is lost. So we need some good reinitialization, so which isn't still an issue. Good. How much time do I still have?
Half an hour.
Half an hour more. Okay, good.
We can stop whenever you want.
Okay, good. Actually, so the next is a bit better, so maybe I'll finish with this and then we can have a break. Okay, so now I'm going to talk about the motion-based methods. So we've looked at appearance and the evolution of appearance. So now we are going to talk about motion. So what's the motivation of using motion directly for recognition? Is that it's supposed to be more invariant to elimination other factors. And also, if appearance does not provide much cues, for example, as in this picture, so can you guess what this picture is representing? Sorry? Right. So if we make it move, so this becomes very clear, right? So this is a strong motivation for using motion. It has been realized a long time ago. So again, so why is it good? So okay, because it's a complementary information to the shape, but also it's more invariant to things like, for example, the clothing, so the color of the clothing and other things, because ideally the motion field should be independent of appearance, so it should be just motion. Of course, in life, in real life, so it does depend on the texture and other things, as I will show next slides, but it is an interesting cue, and it relates to these experiments which I have talked in the beginning. Okay, so how to estimate optical flow? So any of you are familiar with optical flow methods? Good. So I think 10 years ago, this would be half of the people. So optical flow is a quite studied method in the past, and but still it's still a hard problem. So it's the unsolved problem. And so I'm going to spend just 3 slides on optical flow estimation and showing why is it hard and where does it work, where it doesn't work. So what is optical flow? So what you ideally want, we want to estimate the motion field. So what's so there is a 3D motion field in the scene. So when your points move on your body in a 3D, so you can from one time instance to another, so you can generate motion vector, okay, 3D motion vector. And then, so if we imagine all this 3D motion vector, if you project them to the image plane, this would be the motion field. Okay, the motion field is not directly accessible from the images. So instead, what we only can actually do, we can try to establish the correspondences between one frame to another. So this is, well, that's what people try to do. However, it's not always possible. So what the most common assumption to do this correspondence estimation is brightness change constraint, so which says that the change of the color of each pixel from one frame to another is only caused by motion and not by other factors, for example, switching of the light and so on. Okay, so if this constraint is true, so the things become a bit more easier. However, so even in this case, it's not, right. Yeah, so even in this case, so this is not always possible. So, for example, if here's one example where you have a sphere without any texture, and we have a light source. No, so the scene is rotating, but the light source is static. So obviously the image doesn't change. So, however, there is a motion field which we just cannot observe from the image. So here's an opposite situation. If we have a static sphere, again, no texture, and the light source is moving, so we perceive the motion because we tend to match the points from one frame to another, but actually they are caused by the moving light source, not because of the motion of the object. Okay, so these are well-known problems. However, as people, we perceive the motion all the time, so there should be some from 2D signals. So this should be this is a good evidence that motion estimation is not hopeless. So how does it work? So this is one approach. There are several standard ways how to solve the motion estimation. So this is one introduced by Lucas and Kanade in '81. So one can convert this brightness change constraint into mathematical form, and this would look like this. So what this is, what it says that the change of the image brightness multiplied by the vector of the velocity vector is should be equivalent minus temporal gradient of an image. Okay. So I'm not going to derive this, but this is the fact. This is well-known fact. So okay, so if this equation would be solved, so v is unknown. Okay, so this we can measure. This is the image gradient. This is temporal gradient. So if you could solve this, we could get v. Our problem is that v is two-dimensional vector, and this is just one equation. So the problem is under constraint. So what Lucas and Kanade proposed. So if you not just take this measurement in one point, but if you assume that your points in your local region, they all follow the same motion. So basically, the v vector is the same for points in the closed neighborhood. Then, then you can solve it in the least square sense. Okay, and then you can get the v. Okay, so this is a standard thing. Now the problem is, okay, so what are the when we start to aggregate information in the local neighborhood? So the problems are the following: that okay, so what are implicit assumptions we are making is that the brightness change constraints holds. Okay, this we always need. We need okay, we also need a sufficient variation of image gradient, because if all the image gradient in a neighborhood, if they are all the same, we don't gain anything. Okay, and this is actually situation here. So if this is our point, and this is the local neighborhood, and all the image gradients are looked in the point in the same direction, the system is still under constraint. So we assume that we should have the variation in the gradient. And also we assume that the motion should be constant. Okay, we can see where it breaks. So if we have insufficient gradient variation, like in here, right? So this won't work, as we said. So in this case, maybe we want to increase the neighborhood. So of course, if we increase the neighborhood, so eventually we will find some corners and other structures in the image which are with a variation of gradient. However, as more we increase neighborhood, the more chance it is that the vectors, the velocity vectors in the neighborhood, they are not the same anymore. So we will violate the third assumption. Okay, so these are problems, as I said. So optical flow estimation is not solved problem, and probably won't be ever solved completely. Also, so we can imagine now that maybe just reasoning about very local or low-level features like gradients maybe not enough. Maybe we need to know that this is something more about semantics. So this is a part of an object, for example, and if we increase the neighborhood here, then it won't be the same object anymore. So maybe there are different motions. So motion estimation probably goes very high in semantics, and we are not there yet in this computer vision. So, but nevertheless, so there are standard methods, you know, OpenCV probably, so, or other lots of benchmarks, so you can download. If you need a motion estimation, so you can download a reasonable methods and run it, and so it will give good results in many cases. Fine. So okay, actually, so there is a link from this slide to next. So the link is that if our low-level vision doesn't work, so you increase neighborhood, so it corrupts our this stuff. So okay, so we can learn more sophisticated, more high-level models even for motion. And here is one example. So it's a PCA example. So it's actually very similar to what we've seen with the shape, with the mouse shape. The difference that our vector is not the points on the shape, but it's the velocity Vx and Vy. These are velocity vector in the patch. So imagine we have a motion of the mouth. So for each pixel, we have a motion vector, and we put this all into one big vector to represent the motion in the patch in a particular frame. Okay. So this motion is expected to be very noisy, especially because in the mouth we expect lots of violations of our brightness change constraint, because when the mouth opens, this is a violation of this occlusion happens. So the change of pixel values is not just because of the motion; it's because of new structure appears or disappears. So this is a case where motion estimation doesn't work. However, so what we can do, we can measure first lots of these examples, and if we are interested just in shape motion of the mouth, then we can try to learn again the linear PCA basis for this type of motion, and then denoise the flow by projecting forth and back. Okay, so this is a method which has been successfully used. So again, it's a PCA is a generative method. So, but one can try to learn, for example, the different words, like try recognizing the speech by looking at the mouth. So this is one possible method to use. So here is another interesting example of using motion for action recognition. So you've seen this picture before. So now imagine, so this is very low. So the paper is, I think, called there's no name, but it's something like, so recognizing people at a distance. So the size of this person is really 30 pixels. So it's a very low dimensional signal. And imagine, so if we try to do motion estimation of this signal, this is really hard. So it's going to be very noisy. So here is another way to regularize the motion estimation. So say we run some generic optical flow, so we can subdivide, so obtain the flow field. So this is in each pixel we have a velocity vector and so x, y coordinates. So now if we subdivide it into 4, okay, so here it's subdivided into 2 images. One is flow along the x and one is flow along the y. So we can also subdivide this into minus and plus. Okay, this is positive x motion, negative motion, x motion, and so on. And smooth it. Okay, so this is just basically smoothing. So this is a way to regularize. So basically, smoothing removes the noise. Okay, so this is the way to regularize the flow. And actually, so this representation is very close to histograms of optical flow, which I will be talking later. So it is a robust representation, noise robust representation. So what can one do with this? So say if you have 2 sequences, A and B. So for example, if you want to match these 2 sequences, so we can compute the distance. So say if we concatenate all the values here for one frame, so we can compute the distance from one frame to another, for example, L2 distance from every frame, and obtain the matrix like this. So it's a question to you. So do you know why it looks like it looks? So these diagonal things, where they come from? So each sequence has a human motion. So a person is doing something, and sequence A and B, these are 2 different people doing probably something similar. So therefore, the diagonal is expected to be high if they're doing something similar. But there are multiple diagonals. So do you know why it? In which cases it would be look like this, multiple diagonals? Exactly. Yes. So if it's a repetitive motion, so then say after cycle of a gate cycle is so it's about a second. So then we expect the diagonal structures to appear because the motion is self-similar. Okay, and if we know that the motion is self-similar, so we can also denoise this matrix directly. So that's one way to make it more robust to noise and the differences between different motions. So in practice, what this gives, so if we have 2, so this is input sequence, and now if we have so this is input sequence. Now if we record a very large database, so say of football motions of a person, so we can and subdivide it into small clips. So for each frame, we can, or a small chunk of frames in the input sequence, we can find the best matching chunk of videos in our database sequence, and that's what is shown here, right? So it's we see that this is a different person which has been matched to the motion of this person, and although the matching is not perfect, they are quite similar. The actions are quite similar. Okay, so so basically this is nearest neighbor matching. So once we did matching, we can transfer the labels. So if you know this guy is running, so we can say, well, we know in the database if we have labels for all these guys, so we can just transfer labels from a database to the input sequence. So we can, for example, in this paper, they do this nearest neighbor approach to recognizing football actions like walk left, walk right, and so on. Can also do, so this is the same data set which I've shown before. Still quite simple data set, and so they're doing quite better job with these motion descriptors. So here's another recognizing tennis actions. Fine, so this is a summary of what we've seen so far. So I've talked about pose estimation, so some methods for shape and evolution of shapes over time, and motion-based methods for recognizing figures like this. And next half of the lecture, I'm going to talk about space-time methods and going more to recent methods and more realistic data. Okay, thanks.
Thank you.